Okay, time to get started. So, last time... quick reminder, of course, attendance code, attendance quiz, don't forget. So last time we had an exam. Last time we had a lecture, we were talking about this idea of a weighted average, right? And so just a reminder, if you want to take the weighted average of certain values using certain weights, then this is the expression. This is how you plug the numbers in, as it were, to compute that weighted average, all motivated by just kind of a reinterpretation of averaging. I mean, this is just averaging, right? It's kind of a streamlined version of averaging when you want some numbers to count more than others. Okay, we went through this example, grade-related example. Again, the weights are different, but this is pretty much how we're going to do grades in this course. And if you have any detailed further questions about how all this works or how any aspect of grading in this class works, come talk to me, please. I'm very happy to elaborate as much as is needed. Okay, all right. So the big idea of this next thing is that you can do the same thing for a function. If you think about it, a function is a bunch of values. And you could reasonably talk about averaging the values of the function. Problem is, there's infinitely many values of a function, right? So how do we deal with, I can't add up infinitely many things and then divide by infinity. That doesn't work, right? But we can do a different kind of addition, right? We can do an integral. And the big trick is if you want to average the values of a function, you use size in the domain as the weights. And so you see here I'm using the dx's in the position where weights are supposed to go. Okay? So reasonable extension of the above idea, but this is in kind of a continuous way. Now I'll point out a couple of little quickie observations. This denominator here is very easy to compute, right? No problem there. Then I can take this equation and I'm going to cross multiply this denominator up to here. And let me just write down what that gives me. And I want to avoid confusion. So let me sort of cross this off there. We'll put the b minus a there. And then notice what we have is that for an interval from a to b, looking at some function, the average value is the value that makes this area equal to, well, let's see here. Where's the average value on this picture? Well, if the average value is, the colors. The average value is determined as per that formula. If that's the average value, then that just makes the green area equal to this orange area. Ooh, if I can get the thing to cooperate. Right, so it's a nice little alternative take on the average value. I'm going to call this a plausibility check, right? If you determine the average value of a function the way we sort of generalized from the discrete case, you get something that you can motivate in a different way that, again, still pretty much makes sense, right? I think this is a reasonable point of view on what the average should be. Okay, y'all can do the example is very plug and chug. Y'all can read. You can do the same thing in any dimension. Right? So again, average value of the values of a function of two variables. And again, you use the weights, the size in the domain. Now this is a function of two variables. The domain's two-dimensional. Size means area. So again, we're using size in the domain as the weights. Right, so very, very similar idea, kind of a rip-off of the rip-off of the original idea. And again, easy example. The noteworthy thing about this example is that when you write down the corresponding expression, like so, just notice nothing in the statement of the question tells you that you should do that with polar coordinate integral. Right? So this is a heads up kind of a situation, right? So this is all students It is your, I'm going to say, responsibility going forward, right, to constantly be thinking about what's the best way to compute this thing that I'm looking at, right? Don't just go, straight forward at all times and just, the head on a swivel. Look for your options. Constantly be digging around in your toolbox, looking for clever ideas that might make your life easier. And this computation, much easier in polar than it would have been in rectangular. And if you don't believe me, try it in rectangular. I think you'll agree very quickly. All right. Okay, so anyway. Next related idea is the idea of center of mass. And now this is basically just an application of this idea of the average value of a function. We have that formula for average value of a function of two variables, and the thing is, position is a function of position. So x comma y is a function of x and y. Now it's a little bit weird to say it that way, but it's a very simple function, but it is a function. So you can talk about taking the average value of position, location, wherever you might happen to be. This is a one-dimensional example here, of course. And again, using masses as the weights in the usual way. Now this example here is just this is a discrete single variable example. But this is just to illustrate what the concept is. We're going to literally compute the weighted average of position, and the resulting value is called the center of mass. And I will, while I'm here, give you just a real quick take on it, and that is that it's what I'm going to call the balance point. As it turns out, this is not obvious. This is very not obvious. This is worthy of a double check, right? Make sure you don't just trust me on this one. It's not a hard calculation. All you got to do to determine that this is the balance point is just compute the amount of torque that mass on the left will sort of turn counterclockwise, and then compute the corresponding amount of torque that mass on the right applies in the other direction clockwise, and just note that they're equal and opposite. And it's just a matter of writing it down. If you've had a physics class, if you know what torque is, it's highly optional, of course. But it'll turn out that those are equal and opposite, and so the balance point is where the total torque is zero. Anyway, it turns out that center of mass does that. So, neat fact. Okay, so here's the general formula. Again, weighted average of position. We use mass as the weights. It's exactly what you would think it would be. I do have to recognize here that we have now written down an expression that is a little concerning. There's something about this that's new for us. We've never done before. It's our very first time to have an integral where the integrand is a vector. Right? So what does that mean? It's slightly concerning. First time you see some new concept. Turns out that's actually a pretty straightforward idea. If you're doing this is just a double integral, and if the integrand is vector valued, all you do is compute one coordinate at a time. That's exactly what you would think. Exactly what you would hope, I'll say. Okay, so that said, there's your general formula for the center of mass of a two-dimensional region. And let me show you an example. Here's a nice example. Let me go ahead and do this. There we go. So we're going to look at this what we call upper half disk. So it's a half of a disk, and it's the part that's above the x-axis. So where's its center of mass? And now, of course, we also have to talk about how the mass is distributed. So I'm going to assume the density is constant just to keep this first example, more. Let's have less focus on algebraic inconvenience and more focus on how does this process work. All right, so density is 1. That means mass is area. Okay. All right, so per above, the x-coordinate of the center of mass is the weighted average of the x-coordinate. The y-coordinate of the center of mass is the weighted average of the y-coordinate. I'm just copying formulas from from above that we were just looking at. Okay, so now, as it turns out, there's something to say about how we actually compute these integrals. And again, these will usually, certainly in life, these will not announce themselves. So, you write down this integral. Well, let me just focus on the actual integral there. You write down that integral. Notice nothing in the statement of the question, nothing about how this integral is written explicitly instructs you to use a symmetry argument. But you absolutely should, right? This integral, boop, 0 by symmetry, symmetry over the y-axis. Done. Full credit. Right? Just make sure you say 0, make sure you say symmetry, make sure you indicate the axis, make sure you're right. Right? So very, very cool. So this is another thing that I strongly encourage you to constantly be on the lookout for. Right? I mean, this is so much more convenient than other integration techniques when it applies. You should be like excitedly, hopefully, wishful thinking, hoping to find examples that you can use this symmetry. It's totally awesome. Do make sure that you fill in the details. This is, I'm not going to spend class time on this, but definitely make sure to fill in those details. Okay. By the way, as for how you know to do this in the first place, there's different ways to be on the lookout for this sort of thing. You could say, hey, I see an odd power in my exponent. Oh yeah, odd powers, that might be odd. Let's think it through. Let's look for an opportunity here. That'd be one foot in the door. Here's another foot in the door. You can notice that your domain has an obvious line of symmetry. And when you see that your domain is symmetric, that too should be a potential. We may have a winner here, right? And be on the lookout for the possibility that you do have to check the other details. Got to make sure that both the integrand and the domain have the required symmetries, right? But in terms of the tip-off, either one could be a tip-off. Okay, now let's look at the y integral here. This y integral could be computed either of two different ways, depending on how you want to slice it. It's up to you. In both cases, there's square roots involved. In both cases, you're going to have a square root is going to show up in your integrand for your outside integral, but one will show up in a nicer way. And now this is just an example. How often does stuff like this happen? I don't know. Often enough that I think it's worthy of mention. But I'm not saying that this kind of good luck will happen, daily or anything like that. So I just like to make this observation that if you do it this way, so that the very first antiderivative you compute is the y antiderivative of y. Notice the antiderivative becomes y squared. Then you're plugging that square root. You're still plugging in the square root bound, but you're plugging it in to where it will be squared first thing, and then the square root disappears. And that makes life good. So, slight preference, I would say, for doing it this way. Not that you can't do it the other way. The other way is not that bad. You'll end up with a fairly reasonable substitution type integral. That's not that bad either, but I still think the second one here is the winner. Okay. I encourage you to make sure that you can do both of those. Again, just, skill check. Just make sure you're good. Okay. All right, this next thing is, this is one of these topics that, I personally really enjoy talking about this topic. I think this is a beautiful bit of, mostly I like it for the math of it, frankly. But it has powerful physics applications, and most of y'all are engineers. Most of y'all, therefore, need to know physics, and so this is, as a physics example, something that's really useful. The math of it is very fun, but again, tough choices and all that. So you don't have to look through the details of this, but I think it would be healthy to do that if you're so inclined. So that said, the big idea is to understand how to compute kinetic energy, and you may think to yourself, don't we have this formula for kinetic energy? But no, we don't. Not always. This formula only works if you're talking about a mass that is moving linearly. Right? And sometimes that's not the case. Sometimes you might have, for example, let's say a wheel, great big wheel. Where have we seen wheels before? Oh yeah, cars. Right? So this is a big deal. Right? This is in real life. This is a highly relevant question of, let's talk about the amount of energy that's included when you have a wheel that's rotating. Massive, massive deal. And the problem is different points on this wheel are moving with different velocities. So that, bad color choice. This point here is moving with one velocity, but points that are closer to the center are moving slower. So I can't just say, oh, well, look at the total mass of the wheel and multiply by velocity squared. Which velocity? What are you talking about? There's a bunch of different velocities. The axle's not moving at all. The rubber on the extreme, on the edge of the wheel is moving very fast. So you can't use that linear formula. So anyway, you can do a little set up a calculation, do some cool stuff with Riemann sums, and the punchline is that you have, back to this. You have this formula for how to compute the kinetic energy of a rotating mass. You might say the rotational kinetic energy, that formula. So having done that, a clever idea is to make the choice to, let's call that expression I. We're going to give it a name. We're going to call it moment of inertia. And when you do that, the neat result, the neat little punchline is that this formula and this formula look a lot alike. The linear kinetic energy and rotational kinetic energy, again, if you name that accordingly, that's the same structure. And the analogy is actually pretty strong. This thing here is what we call angular speed, sometimes called angular velocity. It's not a vector, so I like to call it angular speed. And it is playing a role in the equation that's totally analogous to the role that linear speed plays in the linear kinetic energy equation. How about that? It's totally analogous. And so with that in mind, I think it's a very reasonable take that this thing called moment of inertia, it's playing the role analogous to mass in this, eyebrow-raisingly impressive analogy. Same structure, we have an analogous notion of speed, and, playing along with that analogy, this seems like a reasonable interpretation of this thing called moment of inertia. So that's the short takeaway that I think is important to retain. It is an angular analog. This thing here, typically denoted with I, is an angular analog of mass, and that's, again, what I think is the good takeaway. Okay, so it's something you need to know how to compute. You should make sure to memorize this formula. There is a catch to this. You'll notice that there is an R there. We use R typically for cylindrical coordinates or polar coordinates, but not here. That's the weird thing about it. This situation, we have used R as the distance from whatever little piece of mass you're looking at, wherever your little piece of mass is, to the axis of rotation. That's what R is, and it's going to be different in every example. So, for example, here's a couple of scenarios. If you've got a mass that is rotating around the z-axis, well, in that case, looking at any little piece of mass like that, yep, R in that case is our good old cylindrical R. But that's assuming we're rotating around the z-axis, and we might not be. We might be rotating around some other line like that. And if I've got, mass at some little location, some little, piece of mass, this distance here is not the cylindrical R for that point. It's just not. Right? Totally different. So that axis might take various different forms, and so this expression might take various different forms. Please don't try to memorize your way out of this problem. There's too many different cases. It's not realistic. Right? So I encourage that every time you use this formula, you should have a reasonable picture, interpret from your picture where your R is, and then write the expression for that R tailored to that picture. And you should think it through from the geometry every time. That's certainly what I do. Okay, so for example, here's a two-dimensional example. And the question says, find the moment of inertia. We're going to start right off with our generic formula for moment of inertia, integral R squared dm. By the way, neat fact, doesn't matter what kind of integral. If you have a two-dimensional, like in this case we have a two-dimensional region, then it's a double integral. If you have a three-dimensional region, it's a triple integral. It's the kind of integral appropriate to whatever your domain is. So the formula for moment of inertia is always integral, whatever's appropriate, integral of R squared dm. Okay. A couple little details to pound out. dm is density times dA. Mass is density times area, right? So there you go. Notice the density is given. So plug that in. Right? And now let's ask the question, what is R? And again, don't just go around memorizing formulas. Doesn't make any sense. You got to think about the specifics of your circumstance. R, in this case, well, here's a little piece of mass, x comma y. And let's see our axis that we're rotating around. We're rotating around the x-axis. So R, remember, is the distance from arbitrary point in your domain, x comma y in this case. Generic position to the axis of rotation. Whatever that distance is, that's your R. And in this case, again, I think once you have the picture, I think the geometry is pretty clear here. That distance is y. Everybody see what happened there? Everybody feel okay about that? Okay. All right. And then, of course, you got to rewrite the double integral as an iterated integral, yada, yada, yada. I will point out one thing for your consideration. Notice the ... here. I do think it's a good idea to actually crank through that. And in particular, this integral, the integral of sine cubed, okay, fine, 2 times sine cubed, it's a little tricky. Now, it's just one clever trick, and it's ultimately pretty straightforward. But there is that little trick in there, and you do want to make sure that these kind of little tricks, make sure you haven't totally forgotten all the little tricks, because it is easy to let that disappear into the past. And unfortunately, integration techniques just keep being useful. And by the way, we have gotten specific feedback from the engineering school to, hey, don't let up on making sure that the students are retaining their integration skills, because we need our students to retain. We're going to be doing a lot of integrals and got to make sure they can still do it. Okay, moving along into chapter 6. This is an exciting moment. Y'all may recall I've been playing up the idea of chapter 6 and 7 since pretty much the start of the course. This is where things start to get a little weird, a little exciting. It's going to be very geometric. It's going to be a lot of sort of concepts that you have to kind of think through. There's going to be a lot of analogous ideas that we'll want to compare and notice the similarities and the contrasts. There's going to be lots of different connections to be aware of. This is we're getting to the point, in other words, where the material is not going to be just one idea after the next. It's going to kind of, instead of being like a stem, it's going to turn into this big, complex flower. And It does make it a little confusing in the sense that there are so many connections in so many different ways, but that is what makes it powerful and therefore kind of beautiful. Okay, so anyway, first step along those lines, we're going to talk about something called a scalar line integral. And ultimately not that big a deal. I'm just going to make an observation here to start. So far, every domain for every kind of integral we have seen to date, the dimension of the domain is the same as the dimension of the world that it lives in. So, for example, when we were doing double integrals, every domain over which we did a double integral, that domain was two-dimensional and it lived in a two-dimensional world. Right? Think about triple integrals. Triple integrals, we have three-dimensional solids. Three-dimensional solids live in a three-dimensional world. Likewise, single variable integrals, of course. So, what I'm going to call dimensionally convenient. And what we're going to find is that this does not always happen. So here's a reasonable counterexample. Let's suppose we're looking at a curve in either the plane or in space. Makes no difference for what we're doing here. Well, if this, for whatever reason, if there's some quantity that accumulates not over an interval, not over an area, but some quantity that accumulates over a curve. Right? So what does that even mean? Let me give you some real world examples of this. Maybe I've got a wire that's bent around into some shape like this, and I want to compute the mass of that wire. Well, I'm going to have to chop that wire up into little pieces. On each piece, I'm going to have to ask how much mass is on that piece, and then I add up over all the pieces. Chop it up, add it up. We basically want to do a Riemann sum. It's just that the domain is all unfamiliarly weird at this point. So it's like we want to do a Riemann sum, we just don't have that kind of Riemann sum. Here's another example that I toyed with at one point. There was a time when I was, we had just gotten married. We were living in a house in North Chapel Hill. We lived there for 1 year. Well, we were house hunting. And it was kind of out in the sort of the countryside. And it was a 4-acre lot. And the driveway was like 150 yards long. And it occurred to me, oh my gosh, if it snowed and if I had to shovel snow off of that driveway, oh my gosh. Woo! And that's an entertaining question. When you have to actually do that, right? Get out there, hurt your back, right? Sitting there shoveling. Wouldn't it be nice to be able to brag about, hey, I moved, 15 tons of snow. It'd be nice to know the answer to that question, right? So you can brag about it. So anyway, if you think about it, such a calculation would be, I could, much more easily address the question on any little piece of the driveway. To shovel 1 foot of driveway, you just look at how deep is the snow and how wide is the driveway, blah, blah, blah. It would be a fairly easy calculation and then add up over the whole curve. So it's a pretty natural question to ask. And so good news, how we write down that Riemann sum, it's not that big a deal. Right? This just kind of piggybacks off of old ideas. On any given little piece, we can talk about the size of that piece of curve. Of course, size is length. And then whatever it is that you're computing, you can talk about whatever that quantity is per unit length. And just like every other integral we've ever seen, right? So single variable integrals give you quantity per unit width times width. Double integrals give you quantity per unit area times area. Triple integrals, quantity per unit volume times volume. Here we are, back to one-dimensional again, quantity per unit length times length. So on any given little piece, the question is easy. Then we add up, make mechanics, how are we actually going to add this up? Is there going to be any shortcuts? We'll worry about that in a second. But logistics assumed, we would just add up over all the pieces. Does that make sense? Good news, there is a really convenient way to compute these. But before we get into how to compute them, I think it's important to recognize and to dwell for a minute on, but what is the thing that we're computing? How do we connect to applications? For example, if I wanted to compute the total mass of snow on this driveway, Q here would be mass, and then this density, this integrand, would be mass of snow per foot of length of the driveway. Okay. All right. Okay, here's the notation. It's just notation, basically shorthand. You can probably imagine, limit of a sum. We're going to abbreviate that with an integral. Well, of course we will. Delta turns into D. Well, sure, we've done that a bunch of times. This notation is, I'm going to say exactly what you would sort of expect. Right, so no surprises there. Even the indication of the domain, right? This domain called C, note, is a subscript, just like we did with double integrals and triple integrals. So, very believable notation. And we have a word for this. The word is scalar line integral. That's called a scalar line integral. The line term is a little unfortunate. Of course, it's a curve, not necessarily a straight line. This is a different usage of the term line. It's line in the sense of like a line drawing. It means curve in this case. Some people call this a path integral because, again, of this sort of unfortunate misuse of the term line. This is just terminology. It's nothing to get upset about. Why do we call it a scalar line integral is a pretty reasonable question, and I'm going to give you an answer that's going to say, question, yeah. Is it exactly the same? Yeah, exactly the same. I can still talk about, by the way, look, I can make it a 3D diagram. Look how easy. I'll just, now it's three-dimensional. Right? So totally the same idea. It's just that now length will be a length that's determined by how it moves in three different directions, and mass per unit length or quantity per unit length is still the same thing. So this works in any dimension. Okay, so why a scalar line integral? The answer is going to seem silly and pointless. But we call it a scalar line integral because the differential is a scalar. Seems like a weird thing to say. Every differential we've ever seen is a scalar, so that seems like an odd. Why do we need to clarify that? And then also, the integrand is a scalar. Which again, up until 15 minutes ago, we never even heard of a vector integrand. Right? So that seems like a oddly fussy distinction. It's going to turn out, a little bit of foreshadowing, in about 20 minutes, or 10, 15 minutes, not long, we're going to see a totally different kind of line integral called a vector line integral that's going to have a vector integrand. It's going to be a vector field. And believe it or not, it's going to have a vector differential. That's just a little foreshadowing. We'll see those details in a few. Okay, scalar line integral. How on earth are we going to compute this thing? I'm doing some sort of an accumulation on a domain like this. It's what I'm going to call an undesirable domain. It's undesirable because I don't know how to compute this thing. It is the domain's fault. We've not seen domains like this before. So, undesirable. Neat observation. We have dealt with undesirable domains previously. That was the whole point of change of variables, was that when you have a stinky domain, all you got to do is view that stinky domain as an image of something and then pull back to an integral on whatever it's the image of. And so the big plan here, details coming momentarily, but the big picture of the plan is to say, well, I've got an undesirable domain. I'm going to view it as an image. I'm going to pull back. And so the plan goes, I'm going to therefore be able to write this mysterious new scalar line integral as just an integral on the t-axis, frankly, a Calc 1 single variable integral. And this is totally going to work. 100% this is going to work. And there's a real simple trick on why this is going to work. Whoops, if I can get my... Oh, what's going on here? Oh, my pen died. Yeah, let me do that. Let me pull out the backup stylus. The big point is if you want a curve to be an image of some function, we have such a function concept in mind in our experience in the past. It's parameterization. That's all it is. Basically, a parameterization of a curve is going to play the role of a change of variables function. Now, there are different details. We're going to talk through the details momentarily. But big picture, parameterizing is like doing a change of variables pullback. Just kind of different dimension, different details accordingly. All right, so y'all know how to parameterize. We're all good at parameterizing. It was a while ago, right? But we did spend some time talking about parameterizing. This would be a great time to go back and polish up your skills on how to parameterize stuff. We're going to be doing a lot of parameterizing of things for, well, pretty obvious reason here. This is how we're going to compute scalar line integrals. Okay, so the big idea then, when you do the pullback, you basically plug in. We just have to figure out what is our stretching factor. The stretching factor is going to be what is it that I multiply by input size, namely dt, to get output size, namely ds. What is the factor that I multiply by there? And if you think about it, we already know that distance is equal to speed times time, so speed must be my stretching factor. That is lucky break. Old news, right? And we wrote this down back in chapter 3. Oh, by the way, y'all remember, so we skipped most of 3.2, right? Except for a couple of important details at the very beginning where we laid out some players, ds and dr and r prime and the unit tangent vector and all that stuff. We kind of talked through various related objects and how they relate to each other. So I want to go back and make sure to review that, make sure you remember all that stuff. So, but in this case, it's a simple matter of distance equals speed times time. Pretty easy old physics concept. So, among all of your plugging in, again, when you do your pullback, position is a function of time. That's just plugging in, right? The only little detail that's a little concerning is how do I relate output size to input size, because I want to turn this into a dt integral, and that stretching factor is just speed. Game over. We win. Simple as that. Now, there is a quick concern that we're going to address before we get into a computation. A couple of computations are coming up real quick. There is a little bit of a worry, though, and that is if you look at this expression here on the right, notice how the parameterization R is in the expression. Now, this should be a little bit concerning. A little bit concerning because the parameterization was not part of the original integral. This original integral was over a curve. Just a dumb curve. not parameterized. It hasn't been parameterized. It's just a curve. When you make up a parameterization, you're making something up. There's many different ways to parameterize. You're picking one arbitrarily, and this would suggest that the answer that we're going to get might depend on how I parameterize, because look, the calculation has the parameterization in it. This is a worry, right? You should be a little concerned that, wait a minute, will the parameterization matter? And neat fact, it does not. This integral is independent of the parameterization. Pick any parameterization you like. It's got to be appropriately regular. Don't do it. You don't want to get into problems with differentiability issues and stuff like that. But if you pick any reasonable parameterization, go crazy. Knock yourself out. Whatever's most convenient for you, it's all good. We'll always get you the same answer. Okay, all right. So that said, we've got that worry addressed. And now let's do some plugging and chugging. And here's our first example. Oh, let's see here. Where's mine? Here it is. Okay, so we have a wire that's following a curve on which there's mass distributed according to a certain given density. So this is one of our original things that we were talking about, that, hey, maybe I'd like to compute this with a line integral. And we're going to ask several related questions. What's the mass? What's the location of the center of mass? What's the moment of inertia around the x-axis? There's a bunch of different calculations that we can do, all in relation to this same wire. And we proceed as follows. Go back up to here, and this is our roadmap. This is how we get stuff done. And notice the very first thing you got to do before you can write this down is you've got to actually parameterize your curve. So that's going to be our first thing, parameterize the curve. Just to get the ball rolling on this example, you'll notice I gave the parameterization. In fact, I defined our curve by parameterizing it. That won't always be the case. Most of the time, you got to do your own parameterizing, right? That's both most of the time in this class and most of the time in life outside of this class. You got to do your own parameterizing. So anyway, parameterization given. So great. Let's plug and chug at this point. Now the first things I'll do, let's talk about just these two. Just these two parts of the calculation, right? So there were several questions. I'm going to talk through how to compute the mass and how to compute the x-coordinate of the center of mass. We have generic expressions. Mass is itself an accumulating quantity. The whole is the sum of the parts. X-coordinate of the center of mass, there's a formula we talked previously about. Write it down. And then, next, note that mass is density times size. Density is given. And then over here, again, mass is density times size. Density, again, given. Cool. All right, let's see now. Wait a minute. This ds thing, we're going to apparently need to know. Let's see, to simplify ds, hang on, ds, we're going to need speed times dt. That's from the previous page. Again, we're just plugging into the formulas on the previous page. So we're going to need to know the speed. Excuse me. So you do have to take your parameterization, compute the velocity, take the magnitude to get the speed. There you go. And now there's a couple of different calculations we're doing here, and they are different calculations of different physical quantities, but they're over the same curve, so they have the same speed. We can use the same parameterization. So that R prime plugs in very nicely, like so. Everybody happy? This is very plug and chug. Okay, a couple other details that we'll talk about while we're here, and I'm going to see if I can zoom out a bit. There we go. So we can get it all on the page. What's the range of values of t for these integrals? Well, the range of values of t is the range of values of t for our parameterization. It is those values of t that trace out the curve, and so it is those values of t that we pull back to. Ditto over there. Okay. And then there's also the question of, hey, what do I do with, for example, this x right there? How do I need to rewrite that in terms of t. How do I write x in terms of t? Well, don't forget that's what a parameterization is. Parameterization is specifically telling you coordinates of location, rectangular coordinates, x and y in this case, as functions of t. And so that tells me that that's that. And wait a minute, what is y? Okay, well, there it is. Y apparently is t squared. So, like so. Likewise on the right. Everybody good? Plug and chug, right? Straight plug and chug. No, I mean, we're just following the formula on the previous page. Okay, so a couple more examples down here. If you want to look through those details, go ahead. I think it's a healthy exercise. You know, think it through. Make sure you believe. Right. Make sure you follow. Okay. All right. Here's another example. Here, I made this one up. It's totally artificial, but you know, kind of relatable. So what I've got here is a fence. Whoops. I've got a fence. You know, kind of like this. And it's sitting on top of the unit circle. So maybe the unit circle is my property line. Right? I'm building a fence on my property line. And I know height of the fence. You know, how tall is the fence depends on position. Now, why would that be? I mean, who knows? Maybe a certain part of my property, I want the fence to be taller because I want more shade, because maybe that's where my house is and I don't want the house to be all hot and stuff, right? Maybe over on the other side of my property, maybe I've got a vegetable garden and I want the sun to help the vegetables grow, so I want the fence lower there. For whatever reason, let's just suppose this is the height formula that we've got. Okay. So, natural question then. What's the area? What's the grand total area of the fence? By the way, very relevant when you're a homeowner, because you're going to, at some point, probably want to stain that fence or paint or whatever your aesthetic preference is. But let's suppose you're going to stain the fence. Well, how much stain will you need to buy? So, reasonable question. Okay, well, the first way we're going to break this down is I'm going to make the observation that the whole is the sum of the parts. So the total amount of area is the sum of what you might call the areas of the individual pickets. Right? Kind of, if you will, slices of area. I don't know if you're familiar with the terminology they call these pickets. So the sum of the pickets gives you the total area, right? All right, what is the area of a picket? Well, I'm going to change my color choice here. The area of a picket, I think it's pretty easy to persuade yourself that it's going to be, well, whatever the height of the fence is there, namely that, it's going to be height times the length along the footprint, right? The length along the unit circle that you move, that picket covers, which you might call the width of the picket. So purple times red, that's what the area is. Everybody buy it? And check it out. We have ourselves a scalar line integral, right? Now, how did I know that it was going to be a scalar line integral? How did I know to use a scalar line integral, as some students ask? Well, I didn't. I didn't think of it as making a choice among options of constructions and then just doing what that choice says. I just wrote down the area. Reality imposed upon me, independent of my will, that the way I'm breaking this area up into pieces is a scalar line integral. It wasn't up to me. I didn't choose that. That just happened. Does that make sense to everybody? Right? So don't think of this in terms of, which kind of integral should I choose? You don't get to choose, right? You write down reality, and reality becomes one of these kinds of integrals. All right. Okay, so that said, as we recall from the last example, you got to parameterize your curve. Let's see, the unit circle is our footprint. That's what we're adding this up over, and here's the whole unit circle just for convenience. Here's how we parameterize the unit circle, and this is old news. Right, this was one of our very first parameterizations we ever wrote down. You want to parameterize the unit circle? Boom. Make sure you have this memorized. This kind of stuff comes up a lot. This particular parameterization comes up a lot, so you want to have this ready to go at a moment's notice. Make sure you have that memorized. Okay. And per the formula on the previous page, we take the derivative, we compute the magnitude, we see that our stretching factor is therefore 1. And then when we do the pullback, clean that up, do the, I know I need this. Let me just, real quick, there we go. When we do the pullback, this ds, representing size on a piece of curve, becomes stretching factor, namely 1, times dt, namely little pieces of size in our pullback space and on the t-axis. And everything else is plugging and chugging. Okay, so we were explicitly given that height is this formula. Notice in the parameterization itself, as always, I've got the formula for how x is a function of t. That's just a matter of writing it down, and we've got ourselves a single variable integral, and we're off to the races. Plug and chug. Again, make sure you can do that. That's a pretty straightforward one, but make sure you can do that. How we doing? Everybody's happy? Okay. All right. Okay, moving along. Next example. Now we're going to go into this with an open mind, kind of innocently, hopefully assuming optimistically that this will turn into a scalar line integral, because we are in fact going to be considering something that's happening over a curve. We've got a curve here, and we know we're going to be chopping up the curve into little pieces. Sure smells like one of these line integrals that we've already kind of dealt with. Again, keep in mind, we're not going to choose to write this as a scalar line integral. We're going to write down reality. Reality dictates what we have to do. We're just going to honestly break down the question. We're hopeful that this will turn into a scalar line integral, but what's going to happen is it's going to turn into something different. And that is what it is. Sometimes reality doesn't behave the way we sort of anticipate. And that's okay. All right, so the big question is to compute work. So y'all remember this old formula. Work is force dot displacement. Remember, this was an improvement on the old high school formula. The old high school formula was kind of silly in retrospect. They treat force as a scalar. What's up with that? Force isn't a scalar. Force has a direction. That means it's a vector. Force is a vector. It was silly of high schools to, context. They can't help it, right? But it is ultimately just quite wrong to treat force as being a scalar. And then again, they had distance, and they treated distance as a scalar. And again, every time you move a distance, you move a distance in a direction. Again, it's fundamentally a vector. So this is the more sort of reasonable formula for how to compute work. But it does still have something left to be improved upon. It assumes that the force is constant. Life doesn't work that way. It assumes also that the displacement is over a straight line path. And, well, yeah, not always going to happen like that, is it? Right? So we got a problem. If we want to generalize this to the more real-world relevant scenario of a curved path on which the force vectors are not constant, right? What do? You can't use that formula up there. Force isn't constant. I don't even know what force to plug in. The displacement, I guess I could talk about the start to the end overall displacement, but that doesn't recognize the fact that I moved in a curve. Maybe that matters. And by the way, it does. Very often. Not always, but very often. All right. So the big idea, as always, is to chop it up into little pieces. In fact, you might say that's sort of the big idea of all integral constructions, is that we take questions we don't know how to answer, and we take our corresponding domain, whatever that is, chop it up into little pieces. That's kind of what we do with integrals. So I'm going to consider one little piece at a time. And on that little piece, notice, on that little piece, the force is approximately constant. Not exactly, but it's pretty close. And notice further, on that little piece, the displacement is it's approximately a straight little path. I mean, it's a short, teeny, tiny little piece of path. It doesn't have enough length. It hasn't had time to really turn or curve much yet. So on that little piece, we, roughly speaking, have a, round off errors aside, constant force over a straight line path. And so on that little piece, we're going to use that formula on that piece. Everybody buy it? And the actual details of this are no big deal. Here's our displacement vector representing, not exactly, right? The curve actually curves a little bit, but close enough, and in the limit, round off error is going to go away. That is our displacement differential. And the force, whatever that is, well, it might not be exactly constant, but again, round off errors are going to go away, and that's approximately anyway what our force is. And on, therefore, that little piece of curve, the work on that little piece of curve, force dot displacement. So F dot dr. And adding up little pieces of work over the whole gives us a grand total amount of work represented by that expression right there. How are we doing so far? Everybody up on board? Now notice, I didn't choose. Right? My hands are tied. If I break it up into little pieces, this is how work is computed. I didn't decide to write down a new mathematical construction. Reality made that happen. I was just kind of along for the ride on that. Is that cool? Everybody see what happened there? Okay. All right. Now, there are different ways to rewrite this, and if you're following along in the lecture notes, you can probably see this coming. I can rewrite this in a different way, and I can rewrite this in a way that will actually kind of make it look like a scalar line integral. And I'm not going to yet, because I don't want it to look like a scalar line integral. In fact, I propose that this is importantly different from a scalar line integral in a really significant and meaningful way. So my opinion, and y'all have heard me talk about this in the past, right? Like, let's see. Oh gosh, when did I do this? The terms integral and antiderivative. They're importantly different, right? They're really importantly different things. So I don't like the term indefinite integral because it blurs the distinction. If you have two things that are importantly different, the fact that they're related doesn't change the fact that they're importantly different. And when you have two importantly different things, you want to use different terms. You want to keep those concepts distinct, even though they're related. So here's the distinction. Here's what's fundamentally different about this question that's not like any scalar line integral we've seen to now. And that is, the curve has what we call an orientation. There is a well-defined direction that I'm going along that curve. Now, the metaphor I like to work with, just I find satisfying myself, is that maybe this is a mountain road. We're climbing, from the base, whatever, to the top of the mountain, let's say. And as you're driving along, you might very reasonably want to know how much gas you're going to burn climbing that mountain. Very important that you're going uphill. Right? If you're going downhill, you're not burning any gas at all. Right? So very importantly, when you want to know how much work it takes, how much energy, in other words, how much gas you're going to burn, you need to know which direction you're going. The direction along this curve matters. And that is distinct from every example we've seen to now. When you're painting a fence, it does not matter whether you paint counterclockwise or clockwise. You're still painting the fence. It still takes the same amount of paint no matter which way you paint. Right? No sense of direction or orientation here. Does not play in at all. Likewise with these examples here. If you want to know how much mass is on a wire, add it up in whatever order you like. Who cares? The orientation doesn't matter. There is no notion of orientation when you're talking about adding up little pieces of mass, or when you're talking about finding the location of the center of mass. There's just no analogous concept there. Right? So this is therefore already a brand new kind of situation where the orientation, which way we're going, matters. It's a new thing. And so I think it's a good thing that this looks different from a scalar line integral. Now, flashing back to the beginning of 3.2, and this is just a recopy. Everything that's on the page here is from section 3.2, the very top of section 3.2. We talked through this back then. You might want to, again, brush off the cobwebs, make sure you remember all these details. One of the things we talked about is that this dr vector can be written in terms of the other players involved in these three different ways. Again, flash back to that discussion, make sure you're fresh on all of that. So this expression, right, this expression here, with this in mind, let's see here, this dr, I can rewrite it in these various different ways. So I got three different ways to write now the same concept, this same new thing, this vector line integral, right? I've got three different ways to write it down. No tricky curves there. That's just kind of plugging in old formulas. And yes, one of them really does look like a scalar line integral, doesn't it? Look at this. We've got integral ds. It looks like a scalar line integral. And some people like that. And as we just discussed, I actively dislike that. The fact that it makes something fundamentally different look the same, this is blurring an important distinction. I think this is I don't want to say it's a bad idea. There are some situations where this is useful, right? But please do not hang your hat on this formula or this expression for vector line integrals. I think it blurs a critical distinction. Okay. All righty. So how to compute? Yes, go ahead. Yeah.
I just had a question for the
Please.
Graph you showed with the work is equal to force.
This up here?
The one above that.
Oh, okay.
What's the...
Yeah.
Because that's a vector field, right?
Yeah.
What does a vector field represent?
Force. Yeah. So forces, every high school physics example, you see the force is a constant, right? And so, as I walk from here to the door, the force is gravity, and it's down, and it's always the exact same for the whole path. This is constant, right? But if the force is, I'm pushing against the wind, and the wind is going in different directions at different places, well, now the force isn't constant anymore.
So is that saying so the vector field is the force at every point on the curve?
Yes, that's right. So exactly. In fact, the force, the vector field, it's not just at every point on the curve, it's also at points that aren't on the curve. But yeah, you're right that it's going to be different at different points on the curve. Okay. Absolutely. Yep. Yeah. Totally. Okay. All right. Let's see here. Yeah. So, So I was going to point out again with the terminology, just closing a loop. I referred when we were talking about scalar line integrals to the fact that there was going to be an integral where the differential is a vector and the integrand is a vector. And here it is. This is it. So this is why we have to make this distinction. This is why we have a separate term, scalar line integral, and a separate term, vector line integral. Now, just a heads up, a little cultural point. Our book does make this distinction. I have always made this distinction. I think it's important. But in practice, day in and day out, when you're working, user of these ideas, at some point it's perfectly obvious to you and everyone you're talking to what kind of a line integral it is, and very often they will drop the distinction and they'll just say, yeah, line integral. And it's supposed to be understood. Well, yeah, it's the kind of line integral that it is, and compute as appropriate, that's all implicit, right? So you will hear the term line integral sometimes, and when that happens, what that means is they're expecting you to know what kind of a line integral based on, what the circumstance is. So, all right. Okay. All righty. So good news. We already know how to compute these, believe it or not. So, in fact, here it is. You want to compute a vector line integral? Well, we just got through talking about how you can rewrite it like that, and check it out. It is a dt integral, single variable integral over an interval on the t-axis. It's plug and chug. Yeah? Okay. All right, so let's compute. Here's an example. How much work does it take? How much work does it take to perform a certain task? And notice I'm moving along a given curve. There's a given force, and the force is not constant, and the curve is not a straight line. And so we've already entertained the question of how to solve this problem, and the answer is vector line integral. So we don't have to reinvent the wheel on this. We can just say, oh yeah, it's vector line integral. Boom. Now here's the little tricky bit. This is an annoying aspect of the real world, but you'll notice that I'm indicating that the force is negative F, and this is just a reality of the world, that when you have something like my glasses here, right? I'm holding my glasses. There are two forces applying on my glasses right now. Gravity is pulling it down. I am pushing it up. I am applying a force to my glasses with my hand that force is in the upward direction to oppose what the planet Earth is doing, which is pulling it in a downward direction. Is that cool? So I'm sorry to report that when you are going to use a formula like this, you got to recognize that there are two forces in question very often. They are opposites of each other. And you've got to think through consciously which one of those two forces is the one that's relevant to what we're doing here. And keep in mind, all of this came out of work equals force dot displacement, and it's understood in this formula that this force is the force that you are applying. If you want to know how much work you perform, you got to talk about the force that you apply. And notice in the phrasing of this question, I didn't give it that way. I gave it as the wind is exerting this force on you. So the wind is blowing in my face. The wind is applying a force that way. I am plodding along, pushing against that force. I am applying the force that way. So, real easy to mess this up, but the force that I was given here, capital F, is not the right force. Minus F is the right force. Is everybody on board with that? As annoying little inconvenience of the way reality works, but that's what we got to do. Okay. Vector line integral, parameterize. Let's see here. By the way, let's talk about the parameterization. We have here the unit circle. Whoops. What happened to my stylus probably just died. Back to my other stylus. Yep, back in business. The unit circle, y'all remember how to parameterize the unit circle. Think it through. Because we're looking at the top half of the unit circle, t only ranges from 0 to pi. Okay. Take a derivative, nothing to it. Start plugging in. There's that derivative. Oh, sorry, I missed it. Sorry. There's that derivative. Right, just plugging that in. Notice before dr is r prime dt, right? That's one of our pat formulas. Let's see, the vector field F was given as that. Don't forget to carry your minus sign along. And if you want to, factor that into the expression, of course, at some point, you're welcome to do that. But don't forget it. And don't forget, furthermore, that the parameterization gives us our coordinates. So the first coordinate of the parameterization is x. So this x right there becomes just cosine t. Everybody see how that plugging in worked? As usual, or I'll say as before, this range of values of t is our bounds. And we've got a plug and chug. Y'all can do it. It turns out to be an easy plug and chug in this case. Okay. All right. Parameterize however you like. With an asterisk. Very important asterisk. You're not parameterizing the curve. You're parameterizing the oriented curve. The orientation is part of the deal. So when you parameterize an oriented curve, you're supposed to you really need to parameterize the way the curve is going, right? So if the curve is oriented that way, if your parameterization is like this, you didn't parameterize the right curve. Correction, you didn't parameterize the correct oriented curve. You got your orientation wrong, and that's going to mess everything up. And the cool realization is the way it messes things up is you're going exactly the wrong direction. There's a cool thing that happens when you're wrong. There's wrong and then there's better wrong. Here we're wrong by exactly a highly predictable factor. And when you're off by exactly a predictable factor, then the right answer, how far your answer is away from the right answer. Your answer will just be off by a minus sign. So that's all that this says down here. This is just a bunch of notation. We're going to use a superscript minus sign to indicate same curve oriented in the opposite direction. If you just turn around and go the other way, in other words, that's what that little superscript means. And all this says here is that, when you go the other way, you'll be off by a minus sign. A very handy little fact. Combination of reasons. So we'll draw the line right here. We'll pick up here on tomorrow. And see y'all later. Have a good one.